Welcome back. So now we're going to get an explicit equation for the resistance of a resistor in terms of various physical properties that we're going to see, including the shape and dimensions of the resistor. So for now, just think of a resistor as being like an object of this shape here. L here is the length of the resistor, and A is the cross-sectional area. Now, the cross-sectional area here is like a rectangle or a square, but the equation will apply to any shape. You could have, let's say, a cylinder, in which case you'd have a circle here. Okay, so how do we get an equation for the resistance? We're going to proceed by finding an equation that relates delta V and I, and therefore, once we have an equation relating delta V and I, then the ratio delta V over I will give us an equation for R. So our goal is to relate delta V and I. Really here, whenever you say delta V here, it's always understood that I'm working with the absolute value so that everything is positive, okay? But I didn't write the absolute value everywhere. Okay, how do we get started? First, a brief review of some concepts from mechanics. Remember the work done by a force. If the force is constant and the motion is in the same direction as the force, then the work done by the force is just the magnitude of the force times the distance over which the particle that is being acted upon by the force is traveling. So force times the distance traveled by the particle equal the work done on the particle. So here, of course, when I say particle, I mean the charges moving in the resistor. This is true only really when the force is in the same direction as the motion. But here, remember, we had a very complicated motion up and down and so on. But on average, the motion is on a straight line in the direction of the force. So this is if you look at the average motion, you can just think of it as being in a straight line direction. Work is force times the distance. By distance here, I take the distance traveled inside the resistor, so I use L. Now in the graph here, you have lowercase l. In my equation, I'm going to use a capital L just because it's more clear. If I use a lowercase l, it might be confused for a current. It looks a bit like an I. So I use capital L for the length of the resistor. So the work done on the charge as it goes through the resistor is the electric force multiplied by the distance traveled in the resistor, which is the length of the resistor. Okay, so work is equal to that. Now recall that work is it's just a change of energy. So the work is the change of electric potential energy in our case. So work is equal to delta U electric. Okay. Again, work equal to force times the distance for straight line motion, and work is equal to a change of potential energy. Those are concepts from mechanics. In our case, the change of electric potential energy is the charge of the particle that is moving. I use E here, which we call E is positive because I still work in terms of those fictitious positive charges. So each of those fictitious positive charges has the charge equal to E, and delta V is the difference of potential applied to the extremities of the resistor. So that's the voltage applied to the resistor. Again, you have an absolute value here, but it's understood I take the absolute value, a positive delta V. So the work is given by this, and the work is given by this also. So F times L is equal to E delta V. If I solve for the force, I get that the force on the charge as it moves through the resistor is E times delta V over L. That's our first equation, so I call it equation star. Notice that it relates a delta V to a force. So if you remember this cartoon from the last video, you have someone applying a force on the charges, and that was in the cartoon it's called the delta V. The voltage applied was someone pushing. So you see the connection here. Really, the delta V applied to a resistor is related to the force pushing on the charges. Okay, so that's our first equation. Keep that one in mind. Now let's go back to motion of charges, remember, it's really chaotic. There's a lot of collisions back and forth. On average, you have a straight motion to the right, but you have all those collisions. Now, I'm going to introduce a new concept, a new quantity, tau. So that's the Greek letter tau here. That would be the average time between collisions. It's an average time because sometimes collisions can take a certain amount of time. It can take a certain while. Other collisions can be happen very close in time. So the time between each successive collision can vary a lot. So let's say you talk here about the average value. Of course, because electrons are bumping into atoms very quickly all over the place, this number here is a very small time. Okay, so it's a time in seconds. Now recall, obviously, F equal ma, you remember that, of course. And remember that for constant acceleration, you have that if you start from rest, if you apply a constant acceleration, the final velocity or the final speed here is the magnitude of the acceleration times the time over which the force is applied. So those two equations, Vf equal at and F equal ma, are familiar from mechanics. Vf equal at is valid only if you start with no initial speed. Vi was 0. Okay, in our case, we're going to use the following equation, which is not obvious at first. Okay, so if you look at that and you're just a bit not uncertain about how to derive that, don't worry too much about it. There is a way to prove that in a more convincing way, but it requires some calculus. So here, just take my word for it. The average speed, so I've used this equation here, but I'm going to use for Vf, I'm going to use the average speed of the charges. It would be the acceleration times the average time between collisions. So average speed is called the acceleration times the average time between collisions. Remember, average speed is what we call the drift speed, and the average time between collisions is tau. So this equation becomes Vd equal A times tau. Therefore, the acceleration is Vd over tau, the average speed divided by the average time between collisions. I have that. Now, F equal ma, so F is equal to m times this. So I get the force is equal to m times Vd over tau. Of course, here I'm always talking about magnitude of vectors. So the magnitude of the force equal to m times the average speed divided by the average time between collisions. Okay, now I'm going to use that. But so I'm going to I showed it here again. But remember, we had an equation for the current. You see, remember the goal. What we're trying to do is that we're trying to get an equation that relates delta V and current. So I like to have current appearing in my equations. Now, what I'm going to do is that Vd here is related to the current through this equation that we saw previously. The current is equal to the number of free charges per meter cube times the elementary charge times the average speed times the cross-sectional area. This A is the area of the resistor. So from this here, I get an equation for Vd, and I use that and I plug it here. Okay, that way I'm getting an equation for the force that contains the current. So we get this. Okay, so I just replace this equation here for Vd in here, and I get this equation for the force. Okay, this is my equation double star. So now what do we have? Remember, our equation star was an equation that contained was an equation for the force. It contained delta V. Here I have an equation for the force that contains the current. So that's what I have. That's what I needed. Now I'm going to set equal the two right-hand side of equation star and double star. Both equations are equations for the force. So they must be equal. The two sides must be equal. That was our first equation for the force, E delta V over L, the length of the resistor. And this is our second equation for the force. These must be equal. So from this equation here, this is equal to that. I solve for delta V. Okay, I isolate delta V, and I get this equation here. Now, this is exactly what we wanted. We have an equation relating delta V and the current. So everything that is here, remember Ohm's law, delta V equal IR. So everything that multiplies I here is the resistance of the resistor. And that's it. That's our key equation. The resistance of a resistor is equal to ml over n e squared a tau. Okay, now m here, what is m? That's the mass of the free charges that are moving. So in our case, what in ordinary circuits, are moving are electrons. So the fictitious charges are positive, but they have the same mass as an electron. So this m is the mass of an electron. L is the length of the resistor, A is the cross-sectional area of the resistor, and you know from previous videos, and tau is the average time between collisions. So again, remember, A is the cross-sectional area of the resistor, L is the length. We have this equation. Now, notice that those factors here depend on the geometry of the resistor. They depend on the shape of the resistor, how big it is, how long it is. These factors don't depend on the size of the resistor. Depends on the mass of the electron, the elementary charge, the density of free electrons, which depends on the material, and the average time between collisions, which also depends on the material. For different materials, the average time between collisions would be different. So what we do is that people write this equation in the following way: R equal rho L over A. The part that depends on the geometry here, we leave here, and everything else that depends on the type of material, we rename that rho. Okay, so it becomes rho here. Whoops. Okay, so so um, so that's the way we write the equation, but that's just the same equation as this. So clearly, what we call rho is just these factors here. Okay, rho is just m over n e squared over times tau. That depends just on the type of material. So let's say for copper, you'll have one value of rho. For aluminum, you have a different value, and so on. Okay, so that's the key results. Those are the three quick key equations. Rho, by the way, that's the Greek letter rho. It's called the resistivity of the material. And the units, you can see it from this equation here. Units are, so this is in ohms. Okay, L over A, this is the length over an area. So this is meters divided by meter squared. So all of that is meter to the minus 1. So rho here must cancel the meters to the minus 1 and give something in ohms. So rho, the units of rho are ohms times meters, not per meter, times meter. Okay. Okay, and now clearly from here you can see that the resistance depends on rho. So the smaller rho is, the better the conductor the material is. Also, the resistance depends on the length of the resistor and is proportional. So if you double the length, you'll double the resistance. That makes sense. If the charges have longer distance to travel through the resistor, there's more resistance because you have to, it's harder for the charges to go through a longer distance when there's a lot of collisions. The resistance is inversely proportional to the cross-sectional area. That makes sense. If you increase the area here, you make it larger, there's more space for the electrons to move, the free charges to move through the resistor. So if you make A larger, there will be less resistance. Also look at this here. Rho is inversely proportional to the density of free electron. That makes sense. If n is very big, that means you have a lot of free charges. So if you have a lot of free charges, you expect to have a good conductor. So a good conductor will have a small rho. So large N means a lot of free charges, a good conductor, so a small rho. What about tau? If you make tau larger, rho is smaller. Okay, so let's think about what that means. If you have a large tau, it means that rho is small, which means you have a good conductor. Does that make sense? Tau is large, you have a good conductor. Well, think about that. Think about what tau means. If you have a large tau, it means that there's a lot of time between collisions, which means you have fewer collisions per second, which means that it's easier for the charges to move through the resistor. So indeed, that makes sense. A large tau means fewer collisions per second, so a better conductor. Now you can look at table 27.2 in the book for different values of rho. So I'll show you that. Okay, this is table 27.2 in the book. You see different values of rho, of resistivity for different, everything is in ohms times meters. So you see for what we use for good conductors, silver, copper, aluminum, gold, and so on, resistivity is very small, 10 to the minus 8 ohms times meters. If you go to very bad conductors or good insulators, then the resistivity gets very large. Like glass is a very, very poor conductor. Resistivity, depending on the type of glass, you have rho of order of 10 to the 10 to 10 to the 14. So this compared to that, you see is about 10 to the 18 times larger than the resistivity of silver. So you see a wide range. Here, all here, you have good conductors, and then you have good insulators here. Okay. Okay, so we're pretty much almost done. Last thing, I'm going to introduce one last concept, which is called the conductivity sigma. So we use the Greek letter sigma. Sigma is defined to be 1 over the resistivity. So it has units of ohm meters minus 1. So if you have a good conductor, you have a small resistivity rho, and a good conductor has a large conductivity sigma. Okay, just a quick definition here. Now, you're all set now to do examples 27.2 and 27.4 in the textbook. You have all the entire solution presented there, so you can check your answers and you can understand all the steps. You should be able to do those two examples, and you should be able to do the quick quizzes 27.2 and 27.3, which are on page 814, I think. The answers to the quick quizzes are at the end of the chapter, so you have the answers. And that's it. We're done with chapter 27. Okay? Thank you.